Good morning, everyone. So welcome to today's class. Yeah, so time is very fast. So we're already the last week. But don't worry, we can still finish all the contents. All right, so recall that last class we learned the Minimax algorithm as well as how to implement the Minimax algorithm from scratch. Actually, this question was already asked in last class by some students. That is for the Minimax algorithm, the AI, if we regard the AI as the max player, then the max always assume that the another player, that's the min player, also plays optimally, right? So that is basically the AI who uses Minimax will just assume that the opponent is also using Minimax. This is the assumption for Minimax algorithm. Then what if the other player does not play optimally? What if the min does not play optimally? Note that in this case, actually, it won't affect that Minimax is still an optimal algorithm. Because just think of that, if the min does not play optimally, and that means only max plays optimally. Actually, max will even do better in this game. Max will win faster if the min does not play optimally. So even though in reality, sometimes like the opponent of the AI does not play optimally, that means the assumption does not hold true, but this doesn't affect that the Minimax is still an optimal algorithm to play the games. All right, then next, let's see some disadvantages of the Minimax. So if you look at the Minimax algorithm, you already noticed that each time if you want to evaluate a root node, then you have to expand the whole game tree. You have to first construct the whole game tree under the root node. And in this case, the tree has a very huge branching factor. That's the number of children at each node, because usually at each step, there are many possible actions to take, and which makes the process of reaching the goal state very, very slow, because you have to first construct the whole tree. And in this case, it can take a long time to evaluate an entire game tree. Right? So after you build the game tree, you need to evaluate them. Then you need to start at the leaf nodes. Leaf nodes is that start from the terminal states and then go up, do some like depth first search until you finish evaluating all the nodes. So let's consider some games such as Go or chess. We know that the search space for Go or chess is very big. In this case, if each step we want the AI to evaluate the whole game tree, then the time consuming will be very much. So that means it's possible that the AI cannot take a move within the limited time. In this case, we may think about that, okay, is there a way that we can try to reduce the search space? That means, is it possible that actually some nodes or some branches, actually they are unnecessary to search? In this case, we try to find this way, like search and evaluation of the unnecessary nodes or branches. Is there any cases that such situation just happen, there are some unnecessary nodes or branches? Because if there are some unnecessary nodes or branches, then definitely they will degrade the overall performance and efficiency of the engine. So, and we already know that both me and Max, the two players, they have lots of choices to decide from. And usually exploring the entire tree is not possible, because we know when we are playing games, there is a restriction of time and space. We cannot just have enough time to evaluate the whole game tree. In this case, we try to improve the Minimax specifically in terms of the computation cost. That is, we try to reduce the search space, try to reduce the time to play at each step. And in this case, we find a solution that is called alpha-beta pruning. So alpha-beta pruning is another algorithm, but actually it's based on Minimax. So the evaluation of the game tree is still running the same mechanism of the Minimax, but the alpha-beta pruning, of course, you'll notice that the keyword is pruning. So that means now it's not the complete game tree, because some nodes or some branches will be pruned in this case. Then let's see what is the alpha-beta pruning algorithm. Let's observe the minimax first. Suppose we have such a game tree. Of course, if we use the minimax algorithm, it provides us with the optimal path. Right, this is an optimal algorithm. But did we really need to do all that work? Did we really need to run the whole minimax algorithm? We can use this game tree as an example. So again, we just try to draw the whole game tree in the whiteboard and see that step by step. Okay, here we only have three levels. So the first is a max. Again, we are trying to decide the move for the max player. After the max player is the min player, and at the end, actually at the end it's just some terminal states. So the terminal states we have this. These are, in total, we have 9 terminal states, so they will be acting as the leaf nodes in this game tree. And then in this layer, we have 3 nodes. They are all the min nodes, and the root node is a max node. So this is our game tree. Alright, so after we draw the same tree, that means in the minimax algorithm, we already finished some steps, right? We already constructed a complete game tree, and we already use the utility function to evaluate all the terminal states. Now all the leaf nodes, they already have the values. And now we will run the minimax algorithm. Minimax algorithm, the initialization, max node will be initialized as negative infinity. For the min node, they will be initialized as positive infinity. Alright, then we do the depth first search. Again, this is just repeating what we have done in last class, starting from the root node. So search the way until we reach some leaf node, and we do backtracking to the parent. Now this parent node, this min node, will receive the value from the child, the nan. So that means the value will be updated as the mean between positive infinity and the new value nan, which is none. And now we continue the depth first search. Since these steps, actually we already done that in last class, so maybe I just quickly omit this, jump over. So at the end, after evaluating all of these 3 children, this min node will get the value 7. Right? So each time it sees a smaller value, it gets updated. So after evaluating all of its children, now this node has the value 7. And then we go back tracking to the parent, go to the root node. So the root node is a max node. The max node will get updated as the negative infinity between the new value it received, that is 7. So now currently this node has a value 7. It's a temporary value. It's not the final value. And we need to continue the depth first search. So now we go to this second child node of the root node and go the way to such a leaf node. And it receives a new value 6. Pass it backtracking to the parent. So this parent node, the min node, will get updated as a minimum between positive infinity and the new value it receives 6, so which is 6. Okay, so this is the crucial moment. So that means now this min node, actually we don't know what is the final value, right? But at least we know this value should be smaller than or equal to 6, right? Since this is a min node, even though we haven't seen the values for all of its children, but at least we have one value for one of its child. So that means, okay, later on, if this min node accepts some smaller value, it will get updated smaller than 6. If all of the other children nodes have the value larger than 6, then this min node will remain at the value 6 because it's a min node. It will definitely select the minimum value from all of its children. So Until now, we don't know the final value, but we already know the upper bound for this mean node is smaller than or equal to 6. This is the upper bound. And then we can look at the root node. The root node is a max node. Max node means that it will select a maximum value from all of its children. Until now, its temporary value is 7. So that means this max node, this root node, already has a choice so that it can be guaranteed with the value 7. That is selecting this, the first action. And that means for the max node, for our player now, the second choice, the second action is not a good one. Because if it takes the second action, then the value it receives will be smaller than or equal to 6. That means actually for our root node, it will never consider the second action. It's a bad action. It already seen somewhere better action to get the value 7. So that means actually we don't need to evaluate all the other children of this mean node because we already know this is not a good action for our root node. So all other children, no need to evaluate them. And this is the concept of pruning. So we will directly prune all the children for this mean node. There are some unnecessary nodes, just no need to evaluate them. Of course, you can continue to evaluate them, but that's just a waste of time, waste of search space. No need to do that. All right, then we go back to the root node. Note that in this case, we don't need to update that because we already know this node is smaller than or equal to 6, which will not be better than this 7. We need to continue the depth first search, right? Then we go to the third branch, go to this leaf node, and receives a value from the child, backtracking to the parent. So this parent, this mean node will get updated to the minimum between positive infinity and 3, which is 3. All right, a mean node. So that means for this mean node, the value will definitely be smaller than or equal to 3 because later on it will select a minimum value. 3, again, is smaller than 7. So that means no need to evaluate all the remaining children for this mean node. This is not a good choice for our root node. Our root node, the max player will never consider to take this action. This action is a bad action which will have the value at most 3, but the max player already sees a better choice to get a value 7. So directly prune all the remaining children and pass back to the root node. So at the end, the root node will see that the best value it can achieve is 7, and the best action it should take is by taking the first action. This is the optimal action, the best action for our max player at this state. And this is the motivation to apply the alpha beta pruning. So basically that if when we're evaluating the game tree using the Minimax algorithm, if we already find that some choice is better, definitely better than other choice, then actually for some worse choices, you no need to explore them, to search them. They can directly be given up. So this is the pruning. So any questions so far related with this example? Great. And yeah, so this example, as we can see, actually we pruned these 4 nodes, these 4 leaf nodes, and we pruned these 4 edges. Explanation is basically what I have shown in the whiteboard in here. And then we get the alpha beta pruning concept. Alpha beta pruning idea is that to prevent ourselves from exploring the branches of the game tree that are not worth exploring. Not worth exploring means that they will have no effect on the final outcome. They are not some optimal path. And alpha beta pruning, we need to define 2 values, alpha and beta. These 2 values, they are used to store the information about the potential of a branch for us or the opponent. So alpha cutoff means that we terminate branch because the max player already has a better opportunity elsewhere. And then we can just prune some worse opportunity. The beta cutoff means that terminates the branch because the main player already has a better opportunity elsewhere, right? So the two players, whenever they already know somewhere else has a better choice, actually they just don't need to evaluate the remaining children nodes for the current node. So we have these two cases to do the cutoff, alpha cutoff and beta cutoff. Then alpha is the value, is the best value found so far along the path for the max. Since it's the best value for max, so it should be the highest value, because max always want to maximize such utility value. And the beta is the best value found so far along the path for mean. Since it's best for mean, so beta should store the lowest value, right? The mean always want to minimize this value. And whenever we find this condition is satisfied, alpha is larger than or equal to beta, then we can prune the branch. Alpha larger than or equal to beta, what does it mean? That means the highest value found so far for the max player is already larger than or equal to the lowest value found so far for the mean player. That actually this will have two possible cases, exactly alpha cutoff and beta cutoff. Alpha larger than or equal to beta, actually depending on whether now it happens in a max node or a min node. If it happens in a min node, that actually is just this case and this case. If it happens for a min node, and that means the max player already has a better choice elsewhere. But if it happens for some max node, and that means beta cutoff, the min player already has some better choice elsewhere. But both of the two cases, alpha cutoff and beta cutoff, are equivalent to this case, alpha larger than or equal to beta. So when we prune the branch, whenever we find that alpha larger than or equal to beta. So these are the concepts of alpha and beta. Next, let's see the procedure of alpha-beta pruning, like how to execute such algorithm. Again, we need to evaluate some node, some game state, and we know a game state is exactly a node in a game tree. So we want to evaluate such a root node in the game tree. And we first define two values, alpha and beta. We need the two values to keep track of the current upper bound. Upper bound is the best score for max, and also the lower bound, which is the best score for mean. Alpha is such upper bound, beta is such lower bound. Later on, they will get updated because they should always keep the current upper bound and the current lower bound. Since later on, they will get updated, so again, we just need to assign some initialization. Initially, the root node has values alpha, beta initialized as negative infinity and positive infinity, right? Alpha, later on, will record the upper bound. So later on, whenever it sees a higher value, it will get updated. So it's better to initialize it at negative infinity so that later on, we can update it properly. And beta, later on, whenever it sees a lower value, it will get updated. So it's better to initialize beta as positive infinity. And know that this initialization of alpha and beta is somehow different with the initialization of node value, because initially only the root node has alpha and beta value. So all other nodes initially they don't have alpha and beta value. Just the root node has such two values. But later on we need to pass this alpha beta value to other nodes when we are doing the depth first search. So next we expand the node depth first until a node that satisfies the cutoff test is reached. Cutoff test is alpha larger than or equal to beta. So we just evaluate using the depth first search until such cutoff test is reached. If the cutoff test is not reached yet, then we just keep expansion using depth first search. And during expansion, we need to pass the current values of alpha and beta of parent down to the child node. So that's why initially only root node has alpha and beta value, because later on, during the depth first search, the current values of alpha and beta will be passed from parent down to the child nodes. And then we evaluate the cutoff nodes. And now we need to update the values of all the nodes that have so far been expanded according to Minimax algorithm. That means during the depth first search, the Minimax is still being executed, just like what we have done before. But during such depth first search, we have some extra tasks to do. Not only Minimax, but we also need to update alpha and beta values. We need to update alpha and beta values of all the nodes that have so far been expanded according to, if it's a max node, then alpha should be updated to the max between alpha and current node value. So that means if the node value is already updated, then if it's a max node, then the alpha should also be updated using this way. It will be updated between the old alpha value and the current new value of this node. And if it's a min node, then the beta should be updated. Beta will be the minimum between the old beta and the current node value, the updated one. And actually, by using these two updating rules, we will make sure that alpha and beta always record the current upper bound and lower bound, because alpha always is a max value, beta is always minimum value. And we need to prune all the children of any node whose alpha larger than or equal to beta. This is a cutoff. We have to do the pruning. And because whenever this condition is satisfied, then that means the max player or the min player, they already have some better choices elsewhere. And all the children of this node, they are some unnecessary nodes. They do not affect the final decision. They are just some, actually they're just some useless nodes because they are not some good choices. After that, we need to backtrack. We need to backtrack to a node that has not been pruned, and then we go back to step 1. If there is no such node to backtrack to, then actually we need to return with the value assigned to the root node, because if there is no node to backtrack to, that means we already finished the depth first search. So this is the procedure of alpha beta pruning, and next we will use this procedure to work on our example. Actually, this is the same example in our whiteboard, but previously we just used the Minimax to run on this game tree. Minimax, and then we get some like motivation, intuitive motivation that why some nodes, they are not worth exploring. And next, we will strictly perform the alpha beta pruning to work on the same tree structure. So let's try to empty all these nodes now. We will work as if it's still just an empty tree structure that has not been evaluated so far. Okay, this is a game tree, and we already know all the leaf nodes values, right? The leaf nodes we just already estimated using the utility function. Suppose they already received the value like this. And next, we perform alpha beta pruning. Alpha beta pruning is some new steps on top of Minimax. So that means what we have done for Minimax, we still need to do it for now. That is, for all the nodes, we still need to initialize their values. The max still is initialized as negative infinity, and for the min nodes, they will still be initialized as positive infinity. All right, and next we need to initialize alpha and beta values. Alpha and beta values, initially they will only be initialized for the root node. So for this root node, alpha beta is initialized as negative infinity and positive infinity. Okay, we finished all the initializations, and then we can do the depth first search. depth first search, starting from the root node, go to the first child. And whenever we do this depth first search, the expansion, don't forget the new step in alpha beta pruning. New step is that we need to pass the current values of alpha and beta down to the child nodes. But that means starting from root node, we go to this min node, and then it immediately accepts alpha and beta value from its parent. So now this min node also has alpha beta value, which is negative infinity, positive infinity. It receives from the parent. And then go to the child node. For leaf node, actually no need to give alpha and beta values to it. If you pass it to the child, it doesn't matter actually, but just no need, because this is already a node that has the value. No need to evaluate it, so just it's okay. Directly go back to the parent. All right. After goes to the parent, we need to do updating, right? First, we update this node value. This node value is positive infinity. After updating, it should be updated to none, right? After it receives a value from its child, the node value is updated from positive infinity to none. And since it's a min node, we also need to update beta value for the min node. Like for min node, we always update beta. For max node, we need to update alpha. It's a min node, so we only update beta. So now this beta will get updated from the minimum between the old value, positive infinity, and the new value of this node. The node value already updated to none, so beta will be updated to none. So that means now alpha beta for this min node is negative infinity and none. And we continue after it receives another value from this child 8. The node itself will be updated to have the value 8 because 8 is smaller than none, right? And this beta will get updated to the minimum between old value none and the new value of this node, which is 8. And it receives the last child value, which is 7. So the node itself will get updated to 7, and the beta will get updated to 7. So know that for the first branch, actually for the first branch, it's always that we, if it's only like has 2 levels for this branch, then actually no need to prune anything because the alpha won't get updated. Alpha will always be negative infinity. So that means basically for this first branch, we can never reach the pruning condition alpha larger than or equal to beta because alpha is negative infinity. So that's why all of these 3 children nodes should be evaluated. Nothing will be pruned for this first branch. And at the end, this node received the value 7. And then backtrack to its parent. After backtracking to its parent, of course, the parent node will get updated to 7. It's a max node. It should accept a higher value. In the meantime, alpha will also get updated, right? This is a max node. We know that for max nodes, we should update alpha value. So now, alpha will get updated from the max between negative infinity and the new value for this node, which is 7. Oh, 7. That means now, alpha beta is updated to 7 positive infinity. For max node, we only need to update alpha, no need to update beta. And now we continue the depth first search. Go to the second branch. This step, the min node should accept alpha and beta from the parent. That means for this min node now, it receives alpha and beta as 7 positive infinity, right? From its parent. Now the parent node has the value 7 positive infinity for alpha beta. It should accept this value. And then we continue. Depth first search goes to this leaf node and backtrack to the parent. Receive the node value 6. So this node get updated to the value 6. And in the meantime, the beta should also get updated. The beta is minimum between positive infinity and the value 6, which is 6. Okay, now the alpha beta for this min node is 7, 6. and we find that 7 larger than or equal to 6, right? So that means currently alpha is larger than or equal to beta. We meet such pruning condition. After that, we have to prune all the remaining children for this node. So that's why these 2 branches will directly be pruned, because the prune condition alpha larger than or equal to beta is already met. And then we go back checking. In this case, note that we don't need to update anything because all other things has been pruned. That means this branch does not affect the final decision. So nothing will be updated here. And then we continue to the 3rd branch. After we expand to this node, it accepts the alpha and the beta value from its parent. So now the alpha beta is 7 positive infinity from its parent, the root node, and then search for this leaf node, backtrack to the mean node. So this node will get updated to 3, this value, and now the beta get updated from the mean between positive infinity and 3, which is 3. And alpha is 7, beta is 3. So again, we find that alpha is larger than or equal to beta at this moment. And for this satisfying condition means that we need to prune all the remaining children for this node. So that's why all these 2 branches will get pruned, because alpha larger than or equal to beta, this condition already satisfied. And then we go back check to the parent node. And note that until now we reached that no such node to backtrack to, right? All of the nodes, they are already being evaluated. We go back to the root node. So we need to assign the value 7 to the max node or root node and select the optimal action. This is the best choice it can get to get the value 7. So this is the whole procedure to run the alpha beta pruning algorithm. All right, so for this whole procedure, actually, you can also see the steps here. So basically, you can see the slides. We also simulated the whole step. That's why sometimes we need to prune. The prune happens here at this step. When we find that alpha larger than or equal to beta, we need to prune all the remaining branches. And also at this step, alpha larger than or equal to beta, we need to prune all the remaining branches. So at the end, we prune these 4 branches. All right, so any question regarding this alpha beta pruning example? Okay, great. It's very similar with the Minimax, right? Basically, just on top of the Minimax, you have to do some extra steps. You need to have some alpha value, beta value. So now, for the game tree, actually for each node, you need to maintain 3 values: node value, alpha value, and beta value. And note the difference between node value and alpha beta value. Node value is that it gets updated whenever it receives some new value from its children. For alpha and beta value, the mechanism is that first the node should accept. You can also regard it as the node should inherit the alpha and the beta value from the parent, and then it gets updated whenever it receives some new value from the children. This is the alpha and beta value. And again, for updating each node, whenever it sees a new value, it should get updated. Now with alpha and beta, we should also update alpha and beta. The difference is that for max node, we only update alpha value. For min node, we only update beta value. So this would be the alpha beta pruning example. And next, let's see how to implement the alpha beta pruning again from scratch. We just only need to replace. Previously, we already implemented the Minimax from scratch. So we just need to replace the previous Minimax function with the Minimax alpha beta pruning. So these 2 arguments, we keep them. The board is a current game state. We need to give it as input. And the player who is playing for this step, we need to keep it. We have some 2 new arguments here, alpha and beta. That's the alpha and beta value for this node. Alpha initialized as negative infinity and beta initialized as positive infinity. Alright, we still define a global variable count. This is like how many times we recursively call this function minimax alpha beta pruning. Each time we call this function, count will be added with 1 so that it just correctly record the times. And then we check the game, right? Given the current game state, we need to check if any player already wins, like whether the game already ends. If the result is not 2, then that means the game already ended. Then we can return the result. The result actually is the utility function. It can return 1, negative 1, or 0. If 1, then that means the winner is the AI. If it's negative 1, then human wins. If it's 0, then there is a game draw. Alright, if after this code is still running, and that means the game hasn't ended, then we need to decide which move to take. We separate into the two cases because for the two cases they will be different. We know that if it's a max player, we need to update alpha value. If it's a min player, we need to update the beta value. So here we directly separate two cases. If player equal to 1, that's the max player's move, and for else is the min player's move. So let's see the max player's move. If player is 1, we initialize the node value as negative infinity. It's a max node. Negative infinity as initialization, and then we check all board locations. That means we want to expand the current node to some children nodes by considering all the possible actions. So for all these possible actions, that's for I in this board range from 0 to 9. If board I is 0, then that means the cell is empty. That it's a legal action. We can put a mark here. And then we just try to put the player's mark at this cell. That board I be player. Just try this step. And next, we first get the minimax. Minimax value now is recursively calling the function itself minimax alpha beta pruning for the next player, right? So that means we pass the board, the game state, to the next player, to the minimax alpha beta pruning, and let the player be the alternative player, player times negative 1, and we pass alpha and beta to the recursive call. This is exactly equivalent as we need to pass the alpha beta value from the parent node to a child node, right? So when we expand the node, we pass alpha and beta to the child node. Recursively call the minimax alpha beta pruning. And after that, it will return a value. The returned value will be compiled with the node value. Since the player is 1 now, it's a max player, so the node value should be updated from the max between the old value with the new value it accepts from the child nodes, and then get updated to the value. So basically this step is the minimax updates. To update the node value, next, don't forget to update alpha value. Since it's a max node, we also need to update alpha. The alpha will be the max between alpha and value. Okay, alpha always keeps the upper bounds. Then we need to undo the try because we just want to try what value can we get if we put the mark here. We are not really want to just want to put here. So undo the try, let board I be 0 again. And then we need to check the pruning condition. If alpha larger than or equal to beta, if the pruning condition is satisfied, we need to break. Break means that we directly break from the for loop. And what is this for loop? This for loop is that for the current node, we expand it into different children, different branches by considering the possible actions. If we break this for loop, then that means no need to expand the node for the remaining branches. No need to evaluate the remaining children for this node. This is exactly the pruning. By breaking the for loop, is exactly pruning all the remaining children for the current node. This is for player equal to 1, the max player's case. Then for min player's case is very similar. Just we need to update beta value and using the minimum. So else, if it's a min player, then the value should be initialized as positive infinity. And then for I in range 0 to 9, if board I is 0, so this is a legal action we can take. And then we try to put the mark here, let board I be player, and then we recursively call the function itself to evaluate its child node. So call this minimax alpha beta pruning the current board and the other player and alpha and beta. Again, we need to pass the alpha and beta value from parent node to the child node. After receives the value from its child, get updated from the minimum between the old value and the new value to assign the value for this node. And since it's a min node, we need to also update the beta value. So let beta be the minimum between beta and value, and then undo the child. Let board I be 0. We also need to check the pruning condition. If we find that alpha larger than or equal to beta, then we need to break the whole for loop. Means that we need to prune all the remaining branches for the current node. After that, we finish it evaluating the node, and then we return the value. Note that the value is already updated in this if condition and this else condition. So if it's a max player, then the value will always get updated to the maximum value. If it's the min player, then the value will always get updated to the min value. So at the end, we return the value for the current root node. This is the revised version compared with the previous minimax. Now the minimax alpha beta pruning, we get added 2 values, alpha and beta, and also we need to maintain how to update the 2 values. Alright, so basically you just need to replace the previous minimax function with the new minimax alpha beta pruning function, and also you can also try to play with AI in Google Cloud. You will find that the AI still has the same behavior, right? The alpha beta pruning is again an optimal algorithm for AI to play games. It always returns the best action, so you cannot beat this AI. The best result you can get is to end with a game draw. But this has some difference with the previous minimax, is that if you compare the global variables count, you will find that after performing with alpha beta pruning, the count is reduced a lot. So that means previously in Minimax, the recursive call of the algorithm itself will recursively call many times, because for all the nodes in such a game tree, it needs to be evaluated. But now with the alpha beta pruning, the count will get decreased because some nodes are already pruned according to the alpha beta this pruning condition. So this count is reduced a lot. And since tic-tac-toe is just a very simple game, so possibly you don't sense that it reduces the computation time a lot. But if the alpha beta pruning is implemented in some complicated games, then actually we can also find that the game, each step, the time will get reduced for the AI to take the actions after applying alpha beta pruning, because it reduced the search space a lot. Alright, so any questions so far regarding the alpha beta pruning implementation? Great, if no question, then let's take a 5 minutes break. After that, we will continue with some new problems and limitations with the alpha beta pruning. All right, let's come back to the class. So this will be exercise left for you after class. This game tree actually we already worked on that previously. In last class, we tried to use the Minimax to work on this game tree. After class, you can try that whether you know how to apply alpha beta pruning for this game tree. Note that the optimal move for the tic-tac-toe example, if you are using Minimax pruning, Minimax algorithm with the alpha beta pruning, will still be the same with previous Minimax. That is, the best action it should take at this game state is still the second choice after you try that. But some nodes, some branches may get pruned if you apply alpha beta pruning, so you can try that. If you find that after alpha beta pruning, the decision changed, then possibly there is something wrong in your execution of the alpha beta pruning, because alpha beta pruning will never change the optimal choice. It won't change which action to take. It won't change the final root node. That's why we can prune some nodes, just because these nodes won't affect the final decision. So know that the optimal move should be the same with Minimax. Then let's see some analysis of the alpha beta pruning advantages. Advantages is very significant, actually. We already see that from the motivation, right? It plays a great role in reducing the number of nodes which are found out by the Minimax. In Minimax, we have to evaluate all the nodes, but in alpha beta pruning, some nodes are just pruned. And when one chance or option is found at a minimum, it stops assessing a move and save some time. This method also helps to improve the search procedure in an effective way. So now the memory is reduced and also the computation time is reduced, so which is very good. But still, there are some disadvantages and limitations of the alpha beta pruning. So of course, alpha beta prunes large parts of the search tree, but still, the alpha beta pruning relies on that it needs to at least search all the way to terminal states, right? It still follows the depth first search. That means it must go to some leaf node to receive a value. Of course, in our example, this tree is quite shallow. We only have like 3 levels. What if the tree is very, very deep? Then using the depth first search still is very slow if it's a very deep tree, because the alpha beta pruning still it has to go to all the way until it reaches some terminal states, reach the leaf node. And know that for some games, the moves must be made in some reasonable amount of time. That means even with the alpha beta pruning, if the game tree is too deep, then still it costs lots of time and may just exceed the time limits to play a game. In this case, we have to find some approaches to remedy the problem. That means we cannot use too much time for one decision, right? We cannot, if it's very deep, we cannot just spend all the time to reach the leaf node and then pass it back level by level until we evaluate the root node. Still, it's very slow. The approach to remedy the problem is quite simple. Just set a depth limit. Set a depth limit so that we constrain that we will only search the game tree until we reach such depth limits. And some problems already occurred. When we reach the depth limit, it may not be a leaf node. If it's not a leaf node, then that means we cannot use utility function to evaluate that, right? For example, here. Suppose we just set the depth limit as 2. So starting from the root node, we will only search for depth 2. So that means for the depth first search, starting from this root node, we go to this way and go to this node and we meet the depth limit. We won't continue search. But this is not a terminal state, right? If the game has such state, we don't know who wins because the game is still going on. We don't know what will be the results if we don't see the next move. This problem occurs. Now the utility function cannot be used because it's not a terminal state. Then how should we estimate some non-terminal game states? Here we need to use the heuristic evaluation function. So it's an evaluation function using the heuristics. So that means even though the game state is not a terminal state, but somehow we use some heuristics to evaluate what is the possible value for this node. The heuristic evaluation function is the estimated desirability or utility of position. It's just some estimated. It's not the correct utility. The correct utility can only be accessible at terminal state. This is just estimated. Note that the heuristic evaluation function, of course, it should correlate with the actual chance of winning. Even though it may not be 100% perfectly matched with the actual chance, but at least it should correlate with the actual chance of winning. And note that if we use such approach to remedy the problem, then it's not an optimal algorithm, because it's possible that the heuristic evaluation function cannot very accurately reflect the utility function. So it's not an optimal algorithm. It's just an algorithm trying to estimate what should be the optimal move. Next, let's see what is the heuristic evaluation function and how should we design such evaluation function. So here an evaluation function returns an estimate of the expected utility of the game from a given position. We have some requirements. We do have some requirements to design the good evaluation function, right? You cannot just arbitrarily design an evaluation function, then possibly the AI just perform the game very badly. The requirements first, the computation of evaluation function values should be efficient. Otherwise, it's meaningless to design some evaluation function, right? We design evaluation function because we don't want to search the game tree until the deepest level. We want to save some time. So that means the evaluation function value, the computation itself should already be efficient to save this time. And second requirement, the evaluation function should agree with the utility function on terminal states. So basically that means if it's a terminal state, then the evaluation function should return the same value with the utility function. The utility function is some already fixed. We know that already accurately reflect the winning chance. So at least in terminal states, they should match with each other. And for other non-terminal states, the evaluation function should accurately reflect the chances of winning. These are the requirements that we design the evaluation function. Most game playing programs they will use such evaluation function because most of the game playing programs, they will set some depth limits in order to fulfill the time limit. In this case, they have to design the evaluation function. Usually they use this weighted linear function as like Wi times Fi, the summation. So the F are some features of the game position or the game states. For example, if you are playing chess, then possibly the features is the number of queens in this chess game. They will extract, of course it depends on specific games. Different games will have different features. They need to extract the useful features from the game states. And all these Fi from F1 to F1, they are some features of the game state, and W are the weights that measures the importance of the corresponding features. If you believe some feature is very important, then you should assign higher weights Wi to such feature Fi. And note that usually it's not, of course, the AI developers can also try to design such evaluation function, but actually sometimes still people want the program to automatically learn some good evaluation function from the past experience, right? Like after playing many rounds of games, ideally the programs should learn what is a good evaluation function automatically. And this is a promising new direction in the research study. So if you're interested, maybe later on you can also try to study in this new direction, very promising. That is when playing games, or let the AI play the games, how to design the evaluation function, and when this AI is given some initial design of the evaluation function, how to let the AI automatically learn a better evaluation functions from the experiences that it plays the game with other humans or other AIs. So this evaluation function, yes, the design is not easy, but in tic-tac-toe we will see a relatively easy example. So for tic-tac-toe, this is a commonly used evaluation function. We just call it EP. If P is not a winning position for either player, that is a non-terminal state, then we define the EP as this way. Even though the description is quite long, but actually it's very easy and very efficient to compute. EP is the number of complete rows, columns, or diagonals that are still open for max, minus the number of complete rows, columns, or diagonals that are still open for min. So for example, we can try to draw a game board so that you can understand what is this EP. Maybe just use, use this as an example. The game state is here. Okay, suppose at some moment the game state is like this. Definitely this is not a terminal state, but somehow we need to evaluate what is the score, what is the value for this game state. Then according to this EP, it's the number of complete rows, columns, or diagonals that are still open. Open means that it's possible to be occupied by max in the future. Then the first row is still open for the max. Max is the cross, right? Because currently no cell is occupied in the first row. And the second row is not open because the nodes already put a mark here. The second row is not open for cross. The third row is open. And then the first column is not open, but the second column is open for the cross. The third column is open for the cross. Open means that it's still possible for the cross to occupy. And the two diagonals, they are open for the cross. So that means now the number of the lines, like including rows, columns, and diagonals that are still open for max, after counting, we find that it's 1, 2, 3, 4, 5, 6. And now we need to use it minus the number of lines that are still open for the opponent. Opponent, the min player, the nodes. So let's count how many lines are there. The first row is still open for the nodes, right? No one has occupied that. The second row is not open. The third row is open for the nodes. And the first column is open for the nodes. The second column not open. The cross is already here. And then the third column is open for the nodes. The two diagonals are not open for the nodes because the cross is already at the middle. So it should be 6 minus the complete lines, which is 1, 2, 3, 4, 4, which equals to 2. So that means if a game state is like this, even though it's a non-terminal state, we can still evaluate what is the score. And the score, EP, is 2 for this game state. So we can still evaluate it, even though it's not terminal state. This is for some non-terminal state we evaluate in this way. If P is already a win, that is if P is the game state is already some ending state, the terminal state, then if it's a win for max, then we set EP to be infinity. If P is a win for min, then we set EP is negative infinity. Note that we separate the two cases, the terminal states and non-terminal states. We need to define the terminal states because we need to satisfy the requirement that the evaluation function should agree with the utility function on the terminal states. So usually we just separate the cases of the terminal states to define what is the evaluation function. Just let it be the same value with the utility function. All right, this is how we define the EP. And next we will use tic-tac-toe as an example to illustrate the Minimax algorithm with this evaluation. That means we set some depth limit. Now we set the depth limit to be 2. And we use this evaluation function EP to try to simulate a game. And note that later on, in order to reduce some space, we just eliminated all the symmetric positions. And also, this is just minimax. Note that we don't apply alpha beta pruning, but actually you can also try to apply alpha beta pruning later on by yourself. So starting node is an empty board. It's the max move, the cross move. And then for this starting node, this game state, it can expand to the 3 choices because we eliminate the symmetric position. Symmetric position means that we consider that if we put mark here, basically it's the same or symmetric with we put a mark at the up or the left or the right, they are symmetric positions. So we just leave one node here. So that's why we only expand the root node into 3 children instead of 9 children. So we know there are 9 choices, but some of them are symmetric with each other. We eliminate all the symmetric positions. So in total, we have these 3 possible choices. First, we can try to put the cross mark at the middle or at the bottom or at this left bottom, this corner. All right, and then we need to continue to expand, right? So for this node, we consider what is the choice for the nodes, the opponent, main player. The main player can put to the left or to the left bottom corner, and that's all because we eliminate the symmetric positions. And know that until now we reach the depth limit. We just let the AI has depth limit 2. Now reach the depth limit, it has to evaluate the leaf nodes. The leaf nodes, they are non-terminal states. Non-terminal states, so we have to use the evaluation function EP to evaluate them. So for this game state, actually this is exactly the whiteboard. We already estimated that the evaluation function score is 2. And then for this one, after we apply that evaluation function, we found that it should be 1. There are still 5 lines open for max, and there are 4 lines open for min. So the evaluation function score is 1. So this is how we get the nodes values, the leaf nodes values. And then for the second possible choice, we further expand it into these 5 choices for the nodes. The nodes can take these 5 possible positions. And then again, we just use the evaluation function to evaluate all the leaf nodes values as here. And for the third possible choice for the cross, again, we just expand the node by considering what is the main player's move. There are 5 choices, and we evaluate all of them, of their values using evaluation function EP. After that, we apply the minimax. Apply minimax is that the cross, this is the max player, so it should take the value from the this is the move for the main player. This is the nodes move. So it should take the value from the minimum of his children, so it accepts the value 1. And this node accepts the value -2, the minimum from its children. And this node get the value -1 from the minimum of its children. And at the end, the root node will receive the value 1. This is the max move, so it gets the maximum value of its 3 children, which is 1. And we find that for this case, the optimal move is the first choice by put the mark, the cross mark at the middle of the game board. And after that, we finish the first step, the first move of the max. And imagine that the max just put a mark at the middle, and after that, the nodes put a mark here. That is the second move for max, right? You can consider it's a dynamic game playing process. So that is a max and the min, they're already playing. After the max puts the mark here, this is the optimal decision it just receives. So it decided to put it here. Then the nodes put it here. Then continue, we use the minimax with the depth limit to estimate what should be the best move now. Starting from this game state, we can expand this node into these 4 children. By eliminating the symmetric positions, there are 4 possible choices for the cross, the max player. It can be placed at this corner or the bottom or this right corner or this right position, right cell. After that, we just expand each node. This is a min node, right? This is now the nodes move by considering expanding it to different children nodes. And again, we evaluate all of the terminal states. Not terminal states, this is the leaf nodes, but they're still non-terminal states. So we need to evaluate all of them using the evaluation function and get their values, and then perform the minimax algorithm to evaluate all the nodes in the first steps and then go back to the root node. So after that, the root node received the value 1. And actually there is a tie, right? By taking the mark here or taking the mark here can both guarantee the value 1, so meets a tie. And then just suppose that we randomly break the tie. Whenever we see a tie, randomly break the tie and then select select to put the mark at, sorry, where is the, this is the second move. Yes, this is the, okay, third move. By selecting the mark to put at the right bottom cell, and after that, the nodes put at this cell. So this is the current game state, and we need to decide what is the next move for the max. So it's the third move of max. It's a dynamic game playing process. And after that, it just expands the root node into five possible children, because now it has 5 possible choices. And then further expanding the depth 1 node into the depth 2 nodes by considering the nodes actions. So get all of the game trees until the depth limit 2. After that, evaluate all the leaf nodes. Note that until now, some leaf nodes are already terminal states. For example, for this branch, we have 4 leaf nodes here, and these 3 leaf nodes, they are non-terminal states. Non-terminal states, we still need to use evaluation function to evaluate them. And for this is already a terminal state. And for terminal states, the evaluation function must be the same with utility function. So we get the value negative infinity, because now the nodes, the mean player wins the game. So now it receives the value negative infinity. And for all the leaf nodes, we evaluate them using the evaluation function. Know that when it's terminal state, we need to assign the negative infinity or infinity to it. And then, we backtrack to the parent node to evaluate all the nodes in depth 1, and then backtrack to the root node to evaluate the root node value. After that, it received the value 1. So that means it should take the best move here. It should take the action at this position, the left bottom. In this case, it can be guaranteed with the value 1. In all other choices, actually it received the value negative infinity. So this is the third move. Basically, if AI is playing a game, it just runs in this way. So each time, it's dynamic simulation, right? Each time it needs to take a move. It just starting from the current game state, which is a root node, and then try to estimate the nodes. It won't construct a complete game tree because of the limited time. It usually set a depth limit. For example, here we just set the depth limit as 2. It sets a depth limit, and then for all the leaf nodes, use the evaluation function to evaluate the node values and then do minimax. For this example, you can also try to perform minimax with alpha-beta pruning. If alpha-beta pruning is implemented here, then the search space will be further reduced, and actually the efficiency will get further improved. All right, so any question for this example? Great. At the end of this lecture, we still have a practice problem for you. You can try to apply minimax and then minimax with alpha-beta pruning to evaluate this game tree to assess whether you already know how to run these 2 algorithms, and also you can try to compare your answers with the appended solutions here. All right, if no questions, then I think we can end earlier today. We have a quiz for Minimax, but I guess 5 minutes is not enough for Minimax, so maybe we will start the Minimax, the simple quiz, in next class. Next class, we will also finish the very last lecture, the ethics of AI. So see you in next class.